find the distance from the point 375 to the plane x plus y plus z equals 3. All right. So let's just draw a picture of the situation. Now, this is not necessarily how this plane would be oriented in 3 space, but here's a section of that plane. And this point we know is not on the plane. We can check that real quickly by plugging this in. If we do 3 plus 5 plus 3 plus 7 plus 5, we do not get 3. Since it does not satisfy the equation of the plane, this point is not on the plane, and therefore the distance is not 0. Okay. Ideally, well, this is what I want to do. I want to find the length of the line segment in 3 space that goes from the point that I have, 3, 7, 5, to this point, this plane, x plus y plus z equals 3, in such a way that when it meets the plane, it's perpendicular to the plane. Okay. And here's my first claim. You already know the equation of that line. You know the equation of it. I'm not saying you know how long this line segment is, but you know the equation of the line that goes through this point here, the point that I'm interested in, and this point here on the plane. Okay? Well, what do lines look like? They look like r of t equals r0 plus a scalar t times a direction vector. Well, r0 we wanted to go through 3, 7, 5 plus t, and we know a vector that's perpendicular to this plane. 3, 7, 5, I think I gave. The vector is 1, 1, 1, and you might say, oh, how's that? Well, don't forget how you got your equations of planes in general. So generally, the equation of a plane is ax plus by plus cz plus d equals 0. That came as a result of a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And since x0, y0, and z0 is a point, a times that, b times that, and c times that get absorbed into the constant d. Constant d is all those things together. But you have to remember the meaning of a, b, and c. A, b, and c are the components of the normal vector to the plane. That was the vector that we wanted all our vectors, x minus x0, y minus y0, z minus z0, to be perpendicular to. Right? You should think of the equation of a plane, this thing here, as a dot product between your normal vector, a, b, c, and then all these other vectors that would be perpendicular to it. So that's why the direction vector of this line is 1, 1, 1. Okay. So that's promising. I know the equation of the line that does this. So that line, there's its equation. This is r of t equals. It's right there. Okay. What do I need? I have one point. I need to know what this point is. This. Yep. This point here is the point of intersection between this line and the plane x plus y plus z equals 3. So we can actually solve that. Just a little bit of algebra, we can do it. So let's go do that. Here we go. I think it's helpful to take this line and write it in parametric form. So we can write x equals 3 plus t, y equals 7 plus t, and z equals 5 plus t. That just comes from looking at the components, right? Okay. Well, there you go. This has to be true if we're on the line. This has to be true if we're on the plane. Okay, and here's where things get very pretty. Sub this in, and notice how many variables are you going to have? So you're going to have one variable. So what do we get? We get 3 plus t plus 7 plus t plus 5 plus t equals 3. And that's just one equation, one variable. So 3t plus 15, I believe, yeah. 3 plus 7 plus 5 equals 3. So 3t equals negative 12. T is negative 4. Okay. Now, if you think about that for a minute, you should be, oh, wait a minute, that's not a point. right? We were looking for the point of intersection between the plane and the line. What this is the value of the scalar t at the point of intersection. So actually, we can get the point pretty quickly. All we have to do is take this scalar value, which we know corresponds to the point of intersection, and sub it into these parametric equations and get each of our components. So if we did that, what would we have? We would have x equals 3 plus negative 4. We'd have y equals 7 plus negative 4, and z equals 5 plus negative 4. So that's going to be negative 1, 3, 1. So there's our point of intersection. So negative 1, 3, 1 is the point of intersection. And that's it. We're done now, basically, because we want the distance from the point to the plane. So we wanted the distance from 3, 7, 5 to the point of intersection of that perpendicular line going 3 through 7, 5 and intersecting the plane, which happens there. And that's just a 3D distance formula, and you're done. So d equals the square root of the difference in x's, or 4 squared. The difference in y's is also 4 squared. The difference in z is 4 squared. Okay? Okay. You could say rad 48 if you want, 16 plus 16 plus 16, or you could do this. It's really 3 of the same thing, so you could think of this as 3 times 4 squared, right? Now I'm doing that to be lazy and say, now I really know how to simplify this quickly, right? The square root of 4 squared is 4. So this is 4 rad 3. It's not like a huge time savings. If you had done rad 48 first, you'd have to think to yourself, okay, what perfect square goes into 48, right? It would have been 16 and 3, and you would get the same thing. And if you wrote rad 48, I wouldn't even care. That would be fine, too. So let's continue. Let's consider this another way. Again, here's the problem we're looking at. X plus y plus z equals 3, and the point 3, 7, 5. And we're asking to find the distance. So I'm going to ask us, we're going to think about this now in a different way. All right? So here's that plane again. Okay. Now, somewhere above this plane floating in space is the point.